Okay, today's lesson is again about exponential growth and decay, except this time we're going to look at some of the more practical applications of exponential growth and exponential decay. And you'll see that we have probably more applications than you'd be expecting for exponential growth and decay. Here we have just some definitions along the left-hand side here. So we have exponential growth. That occurs when the quantity increases by the same rate in each period of time. We talked about that in lesson 11-2. We have exponential decay. It occurs when the quantity decreases by the same rate. So the difference between those two are increases for exponential growth and decrease for exponential decay. And then we have compound interest. Compound interest is one that you're really going to see a lot as an adult. Your mortgage compounds. Your mortgage interest is compound interest. Any loans that you take out, school loans, are all compound interest. And investments are also compound interest as well. So compound interest can work for you or against you depending on if you're investing or if you're borrowing money. And compound interest is interest earned on both the principal and the previously earned interest. So that's why it is compound. It's interest that is being earned on both the principal and the previously earned interest. And then finally we have half-life. Half-life, you hear that a lot in science. The half-life of a substance is the time it takes for half of the substance to decay into another substance. So you see that a lot with isotopes, radioactive isotopes, such as uranium and plutonium and things like that, is where you hear about half-life. So for each of those, there's a formula here. And I don't want to go too much into explaining the formula. It's explained about, I think, as well as it could be. But we're going to, right here are the formulas for each one of these. We're simply going to apply the formula for each one in examples below, and that should be all you need moving forward for applications for exponential growth and decay. So, example 1, we have to determine which formula we want to use. It says the original value of a painting is $9,000, and the value increases by 7% each year. Write an exponential function to model this situation, then find the painting's value in 15 years. So as I'm looking at this, there's no interest involved here, so it can't be compound interest. It doesn't mention anything about a half-life, so it cannot be that. And it says that the value is increasing, so it must be just a simple exponential growth function. So moving up here, we remember that right here, exponential growth is a times 1 plus r raised to the t power. So I'm just going to rewrite that here. Y equals a times 1 plus r raised to the t power. And now I can plug those values in. A is my starting value. It's 9,000. 1 plus r, well, that's the r, remember, is the rate as a decimal. So that would be 1 plus 0.07 raised to the t power. We're talking about 15 years. So let's take one more step to simplify this a little bit more. And we're at y equals 9,000 times 1.07 raised to the 15th power. Again, that 1.07, this part right here is greater than 1. That means it's got to be exponential growth. So let's see if we can use our calculator. There we go. So I'm going to take 1.07. I'm going to raise that to the 15th power. And let's call that 2.76. So y equals 9,000 times 2.76. 24,000 $840 is what the painting would be worth after 15 years, which I think personally is rather large considering it started off as a $9,000 painting and it was only increasing by 7% each year. But over 15 years, those 7% add up, and we're at $24,840. So that's exponential growth. The next one, pretty straightforward. It says half-life. Acetine 218 has a half-life of 2 seconds. 2 seconds. Find the amount left after 10 seconds. So we have our given information. We have 500 grams. Time is 10 seconds. The half-life is every 2 seconds. So let's go back up to our formula up here. The half-life. So we are starting with 500 grams. So let's just write the formula first. Let's see. We have A equals P to the 0.5, hence half-life, raised to the T power. Okay, now here's where we got to be a little bit careful with T. T is 2 seconds, so we have to convert that. If T is 2 seconds, then after 10 seconds, we're talking about 5 half-lives. So T is really 5. Okay. So my formula would be A equals, the original amount is 500 times 0.5 raised to the 5th power. And here's where you're going to be surprised how little of it will actually be left over even after 10 seconds. Because .5 raised to the 5th power is going to be 500 times 0.03125, which if you look at that number, it's really a little bit more than 3% of the original amount. So times 500, and we'll have 15.625 grams, because it was actually split in half 5 times over the course of 10 seconds. All right, next we have money invested, compounded quarterly. So clearly this is going to be compound interest. Anytime you see compounded, you know it's compound interest. Let's go grab this equation. This is a little bit complicated equation. Let's see if I can't grab this, bring it down here for reference. There we go. So A is going to be equal to the principal, which was $1,200 times 1 plus, remember the rate is in as a decimal, times n. Now n was the number of times it's being compounded, so compounded quarterly, times n times 3. Okay, which makes sense. The 4 times 3 as an exponent, it's going to be compounded a total of 12 times since it's compounded quarterly over 12 years. So let's simplify this a little bit, make life easier for us. And this will be 1 point something. Let's figure out what that something is. 0.02 divided by 4. We got 0, 0, 5 raised to the 12th power. So 1.005 to the 12th power is we'll just call it 1.06. Okay. And so 100 times 1.06 is equal to $1,272. So you can see that we made $72 in interest in just 3 years, and our interest rate was only 2%. So that's compound interest. And then finally, the last one will be exponential decay. The reason I know that is because right here it says that the population is decreasing by 3%. Decreasing by 3%, again, remember that our formula is pretty much the same as the formula for exponential growth. Right up here, we can even grab it and reuse it with one change. The change being, I'm going to change this plus to a minus. So we have our starting amount, which is 1,700 people. We are decreasing by 3% each year, so that's really just 97. The next year is going to be 97% of what the previous year was. And if that is 2000, it's asking us what the population will be in 2012, which would be 12 years. Okay, so 3% each year. So we have 0.97 raised to the 12th power, and that's where it becomes pretty surprising that after 12 years, what we're really talking about is only 60, we'll just call it 69% of what the population was in the year 2000. So y is going to be equal to 1,700 people times 0.69 equals 1,173 people. And there are your 4 examples of exponential growth and decay. And that should give you everything you need to complete the rest of the remaining examples and your homework. Thank you.